Hello, before we dive into the procedure, observation, and calculation of this experiment, I would like to show you the overall Grignard reaction. So first of all, we prepare our Grignard reagent by adding magnesium to bromobenzene and forms the phenylmagnesium bromide, phenyl Grignard. Then the phenyl Grignard attack the electrophilic carbon of the carbonyl group here from the benzophenone, so the bond break. Nucleophilic addition finish, we ended up with the triphenyl methanolate, which is here. Then we add acid to protonate it and forms the final product, triphenyl methanol. First of all, we need to make sure the reaction vessel and diethyl ether solvents have to be very anhydrous because the Grignard reagent are extremely reactive with the Lewis acids like water, and it has the fast acid-base reaction with it to form the following product, which is a byproduct we don't want, benzene. Then we put 80 mg magnesium metal and crystal of iodine to the reaction vial and warm the reaction vial in a hot plate until the purple iodine vapor is observed. After that, we add 0.1 ml of anhydrous diethyl ether into the through the septum, and iodine dissolves and appears as yellow-brown color. And then we add bromobenzene dropwise to the reaction vial to produce the Grignard reagent. We observe that the yellow-brown color disappears gradually. And we let the reaction vial to cool to room temperature at a benzophenone solution to create a Grignard reaction, and we see the pink color appeared. After that, we add HCl to quench the excess magnesium as well, to form the magnesium chloride, as well as to protonate the alkoxide salt, which is the triphenyl methanolate, to the triphenyl methanol, which is our product. After we reach the acidic environment and the low pH in the solution, we observe the pink color disappeared and solid dissolved, and we hand in our product and step to the next experiment. In part 2, we first add sodium bisulfate to reaction vial to reduce the excess iodine to colorless iodide ion, and we transfer the solution from reaction vial to culture tube, and we add the diethyl and perform the liquid-liquid extraction from there. As we can see from the picture, the aqueous layer is the bottom layer, organic layer is the top layer, and we took the top layer, organic layer out and collected in our new culture tube. Repeat the same step for 3 times. Then we dry the organic layer by anhydrous sodium sulfate, both by adding into the culture tube directly and going through the column, and we collect it in a new culture tube. And then we could perform the thin layer chromatography to our product. The left one was the result I got, and the right one was the one I redrew. Alright, here's the R values calculation of different spots from the result. And through the data, I found my ether sample has a similar R values of both triphenyl methanol and a biphenyl, which means it contains the byproduct biphenyl here. So in order to get rid of biphenyl byproduct, we perform the recrystallization by adding methanol to the culture tube and put it into the hot water bath so that the byproduct biphenyl would dissolve at the 6 degrees Celsius. As a result, we got our final product, pure triphenyl methanol. Then we apply the vacuum filtration to get our final product. In conclusion, first of all, we should decide what is the limiting reagent in our experiment. Here's the calculation, and we found the benzophenone is the limiting reagent because it has the least amount. Then, by applying the calculation, we found our crude isolated percent yield was 51%, which is acceptable. Here's the calculation. And after recrystallization, we got 2 mg of the recrystallized product and the 1.3 as the percent yield, which is pretty low. The reason why I got a poor percent yield of the recrystallized product is because I made a mistake when filtering the product. I used the bigger size of the filter paper instead of the smaller size, so some of my product might just leak through the filter. I would say the result of my experiment is okay because at least I got a similar melting point range to the standard melting point range. And that's pretty much it. Peace out.